Hi everybody. I want to quickly derive a couple of really cool equations for projectile motion that you didn't see last year, but that are going to be really useful to us, particularly in our lab on Thursday, where we investigate the relationship between total flight time and launch angle for a projectile. Before watching this video, it's very important that make sure that you're comfortable with three major takeaways of projectile motion. The first major takeaway is that the horizontal motion, the x motion, is steady rate or constant speed motion. So the only equation that really governs the forward motion of a projectile, the horizontal velocity is constant. I'll put that there. V naught in the x direction is constant. So you just have to use rate times time as distance in order to figure out how far forward a projectile moves. Remember that the vertical motion, the second big takeaway, has acceleration is negative g. And so that is undergoing uniform acceleration. And we use our big three or big five now that we have a few more equations to describe the up-down part of the motion. The y motion we need the equations for uniform acceleration. The third important takeaway here is that if something's launched at a velocity, let's say v naught is the initial speed at some angle, that I need to break that initial velocity up into the horizontal and the vertical components. This one will never change. It's constant. It'll stay the same and just march along forward like nothing's going on. This one, the vertical one, will decrease on the way up and then increase on the way down again. So this is the one that will change because it's accelerating. Those are the big takeaways. If you're not comfortable, you still feel shaky, review 4.4 and take a little time to read through that section before watching the rest of this video. The last thing I want to remind you is that to get v naught x, we write it as v naught cosine theta, where theta is the initial angle. And to get v naught y, we write it as v naught sine of theta. So if we're good with all of that, we can go on and take a look at how to derive the major equations of motion for a projectile, the major equation that we're going to verify in the lab. Okay, let's look at the situation. We're only going to be dealing in this lab with the situation where a projectile is launched at an angle and it lands at exactly the same height at which it was launched, so a ground-to-ground problem. Again, we can label V naught and we can label theta, and it's for this situation that we want to figure out a relationship between t and theta. What's the relationship between flight time and theta, assuming that the one thing we hold constant as a control is the initial launch speed. We're going to launch every time from the same setting on the projectile launcher. We're going to vary the angle and we're going to measure the flight time and see if we can verify this relationship. So first thing we want to do, see if we can write some equations down. One of them is not going to be very useful to us for this relationship, but it's worth writing down, and that is the one for the horizontal range, how far it lands when it's shot at a height and it lands at the same height. Now, since it's constant speed, I can remind myself that the horizontal range, how far it goes forward, is just the horizontal speed times the total time. And I can take that a step further and write that as V naught cosine theta times the time. And again, even though this is a relationship between theta and time, since the range is going to vary with the launch angle, it is not an isolated relationship. So this isn't going to help us with what we want to verify in the lab. To do that, we actually have to look at the vertical component of the motion. But let's keep this in our back pocket because it's going to yield something cool at the end of this video. So let's take a look at equation 2 from the big five. That's the y final equals y initial plus v initial yt plus 1/2 at squared. That's going to tell us about the vertical part of the motion between these 2 points, just rises up and falls back down. Let's plug in our values, calling this the initial point and this the final point. Well, I'm landing at a height equals 0. And I'm starting at a height equals 0. So that looks weird, but it's actually accurate. That's what's happening. My v initial y I can write as v naught sine of theta times the time. And then my acceleration, remember, is negative g because vertically I'm undergoing free fall. So minus 1/2 gt squared. Now, as long as t is not equal to 0, which it's not, I can rearrange this and get a pretty neat result. V naught sine of theta times t equals 1/2 gt squared, and one of my t's go away, and I get V naught sine theta equals 1/2 gt. And since t is what we're measuring and theta is what we're varying, I'm going to solve this for t. T equals 2 V naught over g times sine of theta. That is the relationship that we are going to try to verify in the lab. We're going to measure a bunch of different launch angles and set a bunch of different launch angles and measure a bunch of different times. We'll be able to plot this in an interesting way. And we'll also be able to verify the launch velocity of the launcher, which we're keeping steady. So that's the lab. I want to go one little step further here and go back to this little range equation, though, because it yields a pretty cool result. And you're going to use that result to take your data in a more efficient way. So this range, remember, was V naught cosine theta times the time. What if I took my expression for the time down here and plugged it in for the time up here? What would happen? So my range would be V naught cosine theta times 2 V naught over G sine theta. And now I can simplify that. And I'm going to do it in a particular way because I know what result I'm leading to. So I'm going to do it in a way that's a little algebraically more simple. So R is going to be equal to V naught squared over G, because there's 2 V naughts in there, times 2 cos theta sine theta. Now, you guys, do you remember seeing this trig identity last year? I bet you do, and I bet you were like, when am I ever going to use these trig identities? Well, now's your chance to spontaneously use a trig identity, and you might remember that 2 sine theta cos theta is equal to the sine of 2 theta. This is the equation for the range of a projectile that's launched and lands at the same height at which it was shot. What's interesting about this is if you start plugging in values. If you plug in, for example, 30 degrees for theta, you'll get a value for the range. If you plug in 60 degrees, which is the complement of theta, you'll get the same value for the range. Try it out. Sine of 2 times 30 is the sine of 60. And then if I plug in 60 for theta, I get the sine of 120. The sine of 60 is equal to the sine of 120 because of how the unit circle works. So what we find out is that complementary angles have the same range. So as you're taking data in your lab and you're looking at different launch angles, 10 degrees, 20 degrees, 30 degrees, you might as well measure 10 degrees and 90 degrees at the same time, because they should in theory have the same range and you won't have to mess with your setup. You could take 2 pieces of data without having to move your setup around. So that's kind of cool and a fun little result, and I like it. And it also tells you you can figure out where the maximum range is, which we'll do in class, but what angle actually gives you the maximum value of the range. See if you could figure that out. And if you play golf, you could maybe figure out why certain golf clubs take you further than other ones based on this equation. All right, guys, that's it. I know that was a little long, but I think it really describes everything that's going to happen in the lab. So hopefully this gives you the context that you need.